In addition to the impulsive burn model, an incredibly important tool in preliminary trajectory design is the concept of gravitational assist trajectories, also known as hyperbolic flybys. The idea here is to use the gravitational interaction between your spacecraft and some flyby object, usually one of the major bodies of the solar system, in order to change the heliocentric velocity vector of the spacecraft as it's moving past the flyby object. This method falls into the category of what are known as patched conic approximations, where you compose a single trajectory out of two-body conic sections that are then patched together at various specific points in space. And we will come back in later discussions to what those particular points should be for this analysis. In essence, you want to always have the central body of your two-body orbit being the one that is exerting the most gravitational force on your spacecraft at a given point in time. And there are multiple metrics that we will explore that allow you to calculate an effective region of space around each planetary body in the solar system where it should be treated as a dominant body versus the sun. As indicated by the name, in essence, a hyperbolic flyby is an open orbit about some planetary mass body or some other large object in the solar system. And so the setup is exactly that of our hyperbolic two-body trajectory. Here we have essentially the same figure that we originally looked at when we discussed two-body orbits, except that we have rotated such that one of the asymptotes of the hyperbola is horizontal on the page, with the other asymptote coming down in this direction. Your spacecraft enters the vicinity of the central body, F, which will be the flyby body, with some infinite velocity. Infinite velocity is the velocity at infinity. The specific energy of any orbiting body is equal to its velocity magnitude squared divided by 2 minus the gravitational parameter of the central body it is in orbit about divided by the orbital radius r. If we take the orbital radius to be infinity, then we get the result that the specific energy is equal to this quantity, v infinity squared over 2. Because the specific energy is a constant in a two-body orbit, you can always convert between a value for v infinity and a value for the actual orbital velocity at some finite orbital radius. Your v infinity follows the asymptote of the hyperbola because the hyperbola goes to the asymptote at an infinite distance. And the separation between the asymptote and the parallel line crossing the central body that you are flying about is called the impact parameter. And here we will call it variable d. In some other texts, you will find it called variable b or a number of other things. For us, d is going to be the impact parameter. The angle between the two asymptotes of the hyperbola is known as the turning angle, and we will call that phi here. And we will define another useful angle, theta, not to be confused with our other definitions of theta, such as the argument of latitude. Theta here is the angle between the incoming asymptote and the periapsis direction of the flyby orbit. So the angle between the incoming asymptote and the eccentricity vector direction. The rest of the orbital parameterization is exactly as we've previously defined it. We have an orbital radius with some value r sub p at periapsis, the point at which you're making your closest approach to the flyby planet, and the true anomaly is measured from the eccentricity vector direction to the current orbital radius vector. As usual, we can write specific energy as also being equal to negative mu over 2a. Remember that in the case of hyperbola, a is defined as a strictly negative quantity, and so this will give us a strictly positive specific energy. Equating these two relationships, we can solve for the semi-major axis of our flyby hyperbola and find that it is negative the gravitational parameter of the flyby body divided by the magnitude of the infinite incoming velocity squared. We also know that h squared over mu, the magnitude of the specific angular momentum of our flyby orbit divided by the gravitational parameter of the central body, must be equal to the semi-parameter of the orbit. This applies for hyperbola just as it does for ellipses, and therefore the specific angular momentum is equal to the square root of the gravitational parameter times the semi-major axis times 1 minus the eccentricity squared of the orbit, and is equal to the magnitude of the v infinity incoming vector times the impact parameter d. And this result you get from the fact that the angular momentum must be equal to the magnitude of r cross v. At an infinite r, the position vector is strictly orthogonal to the velocity vector, and so you get just the magnitudes of the separation in the orthogonal direction, which is the quantity that we defined as the impact parameter, times the magnitude of the velocity itself. So we therefore have the gravitational parameter times the semi-major axis times 1 minus the eccentricity squared must be the square of the infinite velocity times the square of the impact parameter. And we can substitute for semi-major axis from this expression. And when we put all of that together and solve for the eccentricity, we find that it is equal to 1 plus the norm of the infinite velocity of the incoming asymptote to the fourth power times the impact parameter squared over the gravitational parameter of the central body squared, all square rooted. At periapse, we have an orbital radius of r sub p, which is equal to the orbital radius when nu is equal to 0, which from our conic section expression we know to be equal to a times 1 minus the eccentricity. Note that all of the sign conventions work out here. A is a strictly negative quantity. E for a hyperbola is strictly greater than 1, making 1 minus e also strictly negative. And so this will be a strictly positive term. As the infinite velocity goes to infinity, which essentially means that as we accelerate our spacecraft to a point where it completely ignores the gravitational effects of the flyby body, the impact parameter goes to the periapse radius. This is the case where the flyby has no effect on the spacecraft at all, and the spacecraft just travels in a completely straight line. Using this result, we can find where we have substituted our expression for the eccentricity into this eccentricity term here, and substituted negative mu over v infinity squared for the semi-major axis, which we get from our energy relationship, and then solving for the impact parameter, eventually get this expression of the impact parameter as a function of the periapse distance and the infinite velocity magnitude. If we further plug this result into our original eccentricity equation and simplify, we will find that we can also write the eccentricity as the magnitude of the v infinity vector, which I will now just call v infinity scalar, times the periapse distance over the gravitational parameter plus 1. Next, we can consider the specific geometry of the system. We note that this angle here has to be the supplement to theta. And we also note that the periapsis direction, the eccentricity vector, must bisect the angle between the two asymptotes. And so this angle here has to be the same as this angle here. We note that these three angles, phi and two quantities of pi minus theta, must sum to a total angle of 180 degrees, or pi. And so we can write pi minus phi is equal to 2 times pi minus that theta angle, which means the turning angle has to be 2 theta minus pi. Therefore, sine of phi over 2 is the same as sine of theta minus pi over 2. And by the trigonometric relationship between sine and cosine, this must be equal to negative cosine of theta. We again consider the case where our orbital radius goes to infinity. Remember, r must be equal to the semiparameter divided by 1 plus e cosine nu. Because the semiparameter for a two-body orbit is constant, as r goes to infinity, 1 plus e cosine nu has to go to 0. In the limit, as r goes to infinity, nu goes to theta. Again, this part you can visualize from the pure geometry of the system. As you're going to an infinite distance away in either direction, you are effectively setting up the system where your radius vector is parallel or anti-parallel to an asymptote, which drives nu to this theta value. So that means that theta must be equal to the arc cosine of negative 1 over e, which we have just discovered is exactly the same as sine phi over 2. So our result is that sine of phi over 2 must be equal to 1 over the eccentricity of your flyby orbit, and we can plug in the eccentricity value that we just discovered in order to solve for the turning angle phi as a function of the periapse radius and the infinite velocity magnitude. Here is a summary of everything that we have just stated. The eccentricity can be written as a function of the impact parameter and the velocity magnitude and the gravitational parameter of the flyby body, which here we're calling mu sub f to make it very clear which gravitational parameter we're talking about. The impact parameter can likewise be written as a function of the periapse radius of the orbit and the infinite incoming velocity magnitude, and therefore eccentricity can be written as a function of only r sub p and v infinity, and the turning angle can be expressed in terms of the eccentricity, and therefore also as a function of the periapse radius and v infinity. The reason why we're making such a point of stating what we can parameterize these equations with is because these are design tools. And so we need a fixed number of inputs in order to iterate over possible designs. The periapse radius is a really good input because it allows you to set a minimum separation during the flyby between your spacecraft and the body it is using to perform the gravitational assist. This is really significant in cases where the body that you're flying around has an atmosphere or has a significant magnetosphere or magnetodisk, like the gas giants and especially Jupiter. Things that can be hazardous to your spacecraft's health if it gets too close, which would lead you to limit the closest approach. Similarly, V infinity is related to energy and therefore is a really good proxy for a full description of the orbit that the spacecraft is on when it enters the vicinity of the flyby object. So we agree that we are able to parameterize everything with just a small number of scalar values, or equivalently with a full vector description in the form of the V infinity velocity vector. However, we haven't yet talked about the benefits of this. And here's where we might run into some conceptual problems. Because remember, we are modeling the flyby as a pure two-body orbit around whatever object is sitting here at F. That means that the specific energy of this hyperbola is entirely constant. We're not thinking about perturbers, we're not thinking about any other interactions, we're talking about a pure two-body orbit of your spacecraft about this body. And so the magnitude of the incoming V infinity vector has to be exactly equal to the magnitude of the departing or V infinity out vector. Performing this hyperbolic flyby cannot gain you any velocity magnitude with respect to this flyby object. The only thing that it can do is to rotate your orbit according to this turning angle in three-dimensional space. Okay, why is that beneficial? Let's consider your overall delta V's. The vector that we've been calling V infinity is the velocity with respect to your flyby body, which let's assume for the sake of argument is a planet. When you enter the vicinity of this body, you're coming in from interplanetary space where you were previously, presumably, on a heliocentric orbit. And so we can write the incoming velocity vector with respect to the sun is equal to the thing that we've been calling V infinity in, which is with respect to the planet, plus the velocity of the planet or flyby body with respect to the sun. And similarly, the V infinity along the outgoing asymptote with respect to the sun is equal to V infinity out plus the velocity of the central body with respect to the sun. These two velocities with respect to the sun are, of course, velocities at different points in time. This one is at the time when your spacecraft enters the region of the flyby object, and we can call that T1. And this one is at the time when it departs, which we will call T2. But let's assume that the flyby occurs relatively quickly. And so the planet does not have time to significantly change its velocity with respect to the sun, making these two approximately equal. Then we can say the total change in velocity, magnitude, with respect to the sun is given by the magnitude of the difference between the V infinity out vector and the V infinity in vector. And these are the ones with respect to the planet. And these two terms cancel out as long as we assume that T1 and T2 are very close in time. And honestly, this is usually the weakest assumption out of all of this because it does take a while to traverse the space around any given object, especially one that has very strong gravitational effects, such as Jupiter. And so this is where typically this model diverges from reality the most, not to mention all of the various other effects. But again, we are using this as a preliminary design tool, and so such divergences from reality are okay as long as we are aware of them. To make this a little bit notationally clearer, we're just going to call this VO and this V sub I, and we can therefore write the heliocentric delta V magnitude is equal to VO minus VI dotted into itself, quantity square rooted. If we carry out this dot product, we get the square root of the norm of VO squared plus the square of the norm of VI squared minus 2 VO dotted into VI. Both of these are exactly equal to the V infinity magnitude. And so these two terms together are just 2 V infinity squared. VO dotted into VI is again equal to V infinity squared magnitude times the cosine of the angle between these two vectors, which is the turning angle. And so this is negative 2 V infinity squared cosine phi. And therefore, the heliocentric delta V magnitude of this flyby maneuver is entirely given by root 2 times V infinity times 1 minus cosine phi, quantity square rooted. As one final simplifying step, recall that the square root of 1 minus cosine of x for any real value x is equal to the square root of 2 times the sine of x over 2. What that means for us is that this expression is the same as twice the V infinity magnitude times sine of the turning angle divided by 2. And recalling that we can write this sine phi over 2 in terms of V infinity and the periapse distance, the entire delta V expression for the heliocentric velocity change due to the flyby becomes 2 V infinity over the quantity 1 plus periapse radius times V infinity squared over mu. The maximum delta V will occur when the derivative of delta V with respect to V infinity is equal to 0. And solving for that, you find that the maximum delta V occurs when the norm of V infinity is equal to the square root of the gravitational parameter of the flyby body divided by the periapse radius, which corresponds to a turning angle of exactly 60 degrees. And so our basic result is that the most delta V with respect to your original central body that you can squeeze out of a flyby will occur if you set up a flyby such that the turning angle is going to be 60 degrees, and the magnitude of the incoming infinite velocity will be the square root of the gravitational parameter of the flyby object divided by the periapse radius. Because the periapse radius must be larger than the body's radius, the absolute maximum delta V that you can accomplish using this model is equal to the square root of the gravitational parameter of the central body divided by its own radius, which is exactly the central body's escape velocity divided by the square root of 2. As a final note, flybys can be used not only to increase the velocity of your spacecraft with respect to its original central body, for example, the sun, but also to decrease that velocity. And you can achieve either effect simply by choosing whether you fly in front of the planet or flyby object along its orbital path, or behind the planet or flyby object along its orbital path. If you're passing behind the flyby object, then it effectively drags you along with it, and so you will increase your heliocentric velocity. If you're passing in front of your flyby object, then it pulls you backwards, and so you are decreasing your heliocentric velocity and your specific energy. Both of these maneuvers are equally important. If we are trying to get as far away from the sun as possible, as quickly as possible, then we will want to increase our velocity and specific energy. But on the other hand, if we are trying to create a stable orbit around some other body in the solar system, we may very well be wishing to shed some velocity and to shed some energy. As a current example, the Bepi-Colombo mission, which is intended to orbit Mercury, is doing a long series of flybys around Mercury itself in order to shed some energy. Mercury is very close to the sun, and so creating stable orbits around it is quite difficult. Other similar flyby maneuvers have been used to inject spacecraft using very little fuel into stable lunar orbits, again, using flybys of the moon itself to accomplish that. And of course, there's any number of examples of deep space missions that have used flybys, either by going inwards towards the sun. So for example, flying by Venus and then the Earth and Venus again, or some various combinations of Venus, Earth, and Mars flybys before making their way out to the outer solar system. And also things going into very deep space, like the New Horizons mission, which used a flyby around Jupiter in order to decrease the amount of time it would take to get to Pluto.